If you have not already, please go ahead and sign in to the science platform at the link displayed on the screen. And maybe I'll even try to copy that into the chat for you as well, if you're not already logged in. Today's lesson is in the usual spot, so you'll be dropped into this directory, notebooks, webinar series. This is lesson 04. We're talking a little bit about flares. And as always, there's two versions. The live version is what I'll be using to type all the code, and the other version has all of the answers already filled in. So follow along however you prefer, and let's get started. Lesson 4, as you might have guessed from the flares name, is going to be talking about flares, but you'll notice I've titled it stellar rotation rates because we're actually going to be focusing on that core astrophysical property, and then we'll be building outwards from there to talk a little bit more about things like flares or other effects that this key property of rotation might have. But before we get into that, let's talk about the objectives of this lesson. So objective 1 is to extract a stellar rotation rate from a TESS light curve. This is actually pretty similar to one of our previous lessons where we were talking about binary star systems. And so now we're actually going to get into looking at signals, periodic signals that actually come from the stars themselves, not from the coincidence of being in a binary orbit. We'll talk a little bit about the Nyquist-Shannon Samping Theorem and how this is going to apply to us when we're trying to find stellar rotation rates. We're going to talk a little bit about the limits on both ends and play around with those so you can understand why those are important. And then we're also going to try to assess the level of correlation between this rotation that we've seen and the flaring rate. Now, the flaring rate itself is an interesting question, and I don't have a learning objective on here about figuring out how we're going to do that. We are going to use a machine learning package called Stella, and we'll talk a little bit about that later in the notebook. But it just didn't quite fit into an hour-long lesson. There was no nice way to demystify machine learning in an hour. So I can point you to some resources that do talk about how you would train such a model, and in particular, train a model to do things like identify flares. But we're not going to cover that now because I think this is a much more interesting way to spend our time. If you see the cool things that this machine learning package can do, then perhaps you'll feel motivated to investigate further and figure out how it works so that it's not just a black box. Objectives out of the way, let us go ahead and proceed to the introduction. This is potentially my favorite line that has ever been written in a Jupyter notebook. Introduction. Stars rotate. Period. Full stop. Just it's a nice blend of simplicity and accuracy. Basically, every star has some kind of rotation, and it's inherently linked to stellar formation. So these big molecular clouds that condense down into stars, even with just a small amount of motion, which they are guaranteed to have, that'll become an ever tighter spin. It's the classic example of a figure skater pulling their arms in. This rotation is going to tell us a lot about how the star has evolved, its magnetic fields, and other important properties. We're going to approximate this by looking at stellar light curves and seeing if we notice any sources of periodicity. And we're doing this classical idea of, if there's some sort of aberration on the surface of the star, so really some kind of star spot, if that passes around the star as the star rotates, you would get these periodic dimming and brightening of the flux, and that would let us know that, that must be the rotation rate of the star. In actuality, stars really aren't like this. Spots come and go. There are other reasons why a star might pulsate, and so our underlying idea isn't quite right, but it's good enough in this situation. And I feel like I say that for all of these notebooks. Please don't take these and try to publish PhD level research. It's just meant to get your feet wet on some of these topics. But if this is something that you're really interested in, and you do end up wanting to extend this, there are 4 separate papers here that will walk you through dynamo theory and the actual physics that is behind these rotating stellar, rotating stars. And so I encourage you to read that if that's something you're interested in, and to build upon this notebook. I think that's all I wanted to say for the background. So we'll go ahead and move to the import statement. There's quite a lot of them, but they're basically all the ones that we've used before. NumPy, Matplotlib, lightkurve, all of those we've used before. The only new one is Stella, and so that is the package I alluded to earlier. It is a purpose-built stellar flare classifier, so it is a type of it's a machine learning algorithm known as a convolutional neural network. And its basic purpose is to say, is this a flare, yes or no? So we'll get into some of those details in a second. So to get started, I am going to walk us through the workflow that by now is probably nauseatingly familiar to many of you, but it is the fundamental thing you will do when you access MAST data, so it never hurts to see it again. We're going to start with our target, which I have selected to be interesting, and we're going to query for TESS lightkurves. Again, the syntax is something that you should be familiar with from previous lessons. So we'll say that our observation is observations dot query criteria. We'll set the target name equal to the tick ID. The provenance name is Spock, and the sequence number is 1. So we just want to make sure that we set Spock to get the mission-produced lightkurves, and sequence number of 1 is arbitrary, but it makes for nice reproducible results. We'll get our products with observations.get product list. Pass in the obs. Our filtered products are observations.filter products. Pass in the products. Pass in the products and pass in the desired filter. Description is lightkurves. And just display the filtered results. Okay, just displaying to make sure this makes sense. I see a TESS lightkurve. I see sector 1. That's enough checking. We got one result. This is what we wanted to see. Now let's open it up. Once again, very familiar syntax. That's why I'm kind of brushing over all of this, but there are recordings available of the first lessons if this is unfamiliar. So we'll do our cloud URIs is observations.get cloud URIs plural. And we'll pass in filtered products. Also, I just want to take a second to say we have some very wonderful AstroQuery developers. The thing that I've been doing with this weird get cloud URIs and making sure to use the plural and then like trimming it down, there was like a weird bug in how it handled AstroPy tables that has since been fixed, but on the platform, that fix is not available because we are locked into like containers of software, and it just hasn't worked out to get the latest version of that. So all of it to say that the actual API is quite nice, and this workaround you will not have to do in the future. Anyway, let's open this cloud URI using with fs.open. See URIs, here comes the weird 0 indexing. Okay, we'll read binary, that's F. Okay, we've got the cloud file handle open. Now with fits.open, pass in that cloud file handle as a read-only option as FTS. And we'll say lightkurve1 is okay. TESS lightkurve file, pass in FTS. Cool. We'll do a quick lc1.plot to make sure that checks out. And indeed it does. You can tell that this one was especially picked to be interesting. And so there's certainly some kind of variability that we see going on here at the bottom, which we will investigate quite shortly. The other thing to notice, and we'll come back to this, are these large peaks here. Looking at them, my first thought would be, oh, a cosmic ray must have hit the detector, or a small micrometeorite occasionally does actually hit test detectors and causes a phenomenon called Arga brightening. So that would be my initial response to this, and I would want to check the data quality flags. Again, we have other tutorials. It just didn't quite fit into this lesson, but it is something important to consider. Is this data actually from my target, or is it an instrumental effect? In this case, I'm telling you it's not. If you check the data quality flags, they're all good. All of this data is, at least according to the TESS mission, real. All right, so we are going to proceed to this finding periodicity. Again, something that I have talked about previously in these lessons, but we'll use a periodogram. Under the hood, periodograms are using Fourier transforms. And the thing that we haven't quite talked about is making sure to set sensible limits for this. And I think I want to spend a little bit more time discussing this in this notebook. One fundamental limitation is the rate at which our data has been sampled. And really, there's two limitations here. So before we actually talk about the sampling theorem, we can very quickly address the other one, which is if you were studying Betelgeuse, for example, and you know that it has interesting pulsations on the order of 2,000 days, a mission like TESS is probably not the right pick because TESS only observes a 27-day cadence. You are not very likely to pick up an oscillation on the order of 2,000 days with a 27-day subset. You just simply have not captured enough of the oscillation to do anything. There's not a particularly satisfying number for us to pick. So in this case, we're just going to set it to the length of an entire test sector, which works. We would reasonably expect to be able to detect periodicity if we saw an entire period of a light curve. So we'll go with that because it is an option that makes sense. You can probably stretch that out a little bit. So, you might be able to extend that further. So with a 27-day window, get beyond 27 days of detect a period beyond 27 days, but it's kind of a tricky situation, so we're not going to go there. The other more important thing is the Nyquist theorem, and this is a fundamental aspect of signal processing. It does not apply just to astronomy. It applies to plenty of things, the most common one being audio. So in order to fully recover a signal at a frequency f, we must sample at a minimum rate of 2f. This is why digital music files or digital audio files sample at a rate of 48,000 hertz. It's because human hearing only extends up to 20,000 hertz if we're being optimistic. And so if you sample a sound wave at 40,000 hertz, you are capable of fully reconstructing that signal. This is why if you listen, I like vinyls, but the people who claim that they just simply sound better have no basis in signal processing or information theory. So vinyl haters out there, you win. You are correct, according to Nyquist and Shannon. At any rate, this is still applicable to us, and I do find this stuff very interesting. I won't ramble on in this lesson, but please, if you're curious, the Vanderplas paper, super good, and the treatment of this stuff is just really excellent. Okay, spiel aside, let's actually set these limits now. What we'll do is we'll say that our maximum period is 28. This is a cool AstroPi units thing. If you do times u dot day, it will just handle that. It will just take care of it for you, and I really do love that. The other thing we'll do is say minimum period. Now, I just talked about the sampling rate, and we actually know what the sampling rate is for TESS. But to highlight why this is important for you to think about this, I'm going to put in a bogus value. Maybe you make a mistake, maybe you look at the wrong sector, and so you have the wrong cadence of things for test data, but we're going to say that it's 20 seconds. We're saying that we're sampling every 20 seconds, so 20 times u dot s. This choice will have consequences later, but we'll come back to it. I'm going to create a periodogram with lc1.normalize. We'll set the unit to parts per million. just because it's a nice thing to, it makes it easier to look at. We'll do the dot to periodogram method. And we're going to pass in the maximum period is the max period that we just typed above. The minimum period is the min period that we typed above. And then we'll want to do a pg.plot, and we'll go ahead and run that. Cool. So this is our plot. I definitely see some pretty strong peaks, especially in this area over here, probably just shy of a day, and not a whole lot happening out here in the larger period area. We're going to do two things. One, I want to know where's this peak, and two, I actually want to kind of zoom in isn't an accurate statement. We're going to do a log-log plot to resolve some of the details in this graph better. Let's start with the best period, so the one with the highest periodogram peak. And to do that, you can actually do pg.period at max power. So 0.761 days. That tracks with the expectation of somewhere under a day, more or less. And now we're going to look at this plot a little bit differently. So we'll do a pg.plot. Scale is log. Got it. Okay, so definitely a lot more detail available here. And maybe the first thing that you notice is that the left side of this graph at the low period / high frequency end of things, it looks kind of noisy or just busy in general, right? What is this? There's this thickness here of the graph versus over here on the right, where it's one single line. The basic reasoning for this is that it's trying to save computational space. So at the low period, high frequency end, we need more points. We need a finer frequency grid to evaluate this on. I think I'd point you at van der Plas again, because there's an excellent treatment of this, but the short story is that in order to resolve peaks at a given period P, you need this grid spacing of 1 over P. You can imagine that as you get to 10 to the -3 and further, this grid spacing requirement becomes very, very computationally intensive because you're evaluating on so many different points. What lightkurve does for you is it does a handy little thing behind the scenes where at the left end of this graph, it's sampling at an extremely high rate, but that tapers off over time because you don't need it to resolve any peaks anymore. And in fact, that's why this line looks so smooth over here. It's actually just composed of fewer points. It's not sliding up and down nearly as often. So that's what's going on here. Just saving computational resources. You can run this cell down below if you want to evaluate this. It's just going to force your computer to do the more computationally expensive result, and you're going to see that you get exactly the same answer. But you can do it. You can show that they are the same thing. So I included the code for you. We're now going to do the exercise. And in this, the task is to identify harmonics. So when we look at periodograms, occasionally you might see something which is a real signal, and then you might see additional peaks, which are secretly an integer multiple of the frequency or an integer multiple of the period, depending on what space you're working in. But they'll be, evenly spaced multiples that really actually aren't signal. They're just part of the processing that's happened. My hint to you is that this is, I think, slightly easier to identify in the frequency space, but you can do this however you like. And the other hint, just so you don't have to spend time flipping through the lightkurve documentation, is that the way to access these values is you can do a PG, the periodogram dot frequency. So that'll give you all of the frequencies. And you can also do a PG dot power, and that will give you all of the powers, meaning the heights on the periodogram, which are expressed in this parts per million unit. So I'll leave both of these up, actually, PG.power, PG.frequency. And that should hopefully be enough to get you started. I'm going to give everybody about 5 or so minutes, and then I will check in. The solution, or rather my solution to this, would be to start by we take a look up here. I can see these peaks are very clearly all above the power, or all above the value of 10 to the 4. And frankly, that is enough. I know I'm going to get these peaks here. I'll probably get these two. Yeah, this one might not show up, but is that one real? Well, we don't know. But we just want to check whether or not these peaks in particular are aliased or are harmonics of each other. So my solution to this would be to say that we're going to create an index I where the periodogram dot power dot value is greater than 10 to the power 4. And I just want the actual numbers in there. And in fact, from here, I think you can do a pretty good proof just by doing a plot dot scatter. So we'll do pg dot frequency dot value at the index, and then we'll do a pg dot power dot value also at the index. And for clarity's sake, we'll do a label frequency. Sure. Now, the thing is, this is a pretty compelling graph. And in fact, I would make the argument that it is so compelling that there is no need for mathematics or additional statistics. This is the greatest possible result when you are trying to do some kind of science, a result which is so good that no mathematics are necessary. It is a wonderful feeling to have something so clear like that, or to make a plot like this and get the comment, well, where are the error bars? And you say, these are the error bars. It is a great feeling to have that level of precision. And in this case, I'm convinced that these are evenly spaced. Of course, I know that they're evenly spaced, and so you really, if you really did want to check for subtle differences, some approaches you might have taken would be to scan. So you could loop through these looking for a change in frequency greater than 100, 200, whatever your choice is, and you would be able to identify where exactly these peaks are falling. And then you could either collapse them all and take an average and look at the spacing. You could just look at the first and the last. It really doesn't matter. You're going to get that they are evenly spaced either way. But those are some more rigorous approaches that you could take. But I'm convinced this looks great. Now, I did mention earlier that the choice that we had above has consequences, and the consequences of that are the following. We didn't really set a very good limit. So I think what we'll do is we'll go through this breakup speed section first, and then we're going to talk a little bit about what we could have done earlier. We would still have to do this anyway, so let's dive into it, but then we'll come to the final conclusion. So enforcing a breakup speed limit. This is not relationship advice for toxic people. This is stars spinning themselves to pieces. And the basic principle here is that if you were to look at this graph and think to yourself, now wait a minute, could these peaks be actual features of the stars? Might one of these peaks be the real stellar rotation rate? The answer is quite simply no. And the reason for that answer, as is the reason for many answers, is physics. It just doesn't make sense to see a star rotating this fast. And in fact, we can actually show that pretty simply by setting, or in a straightforward way, that is, by just setting two things equal. One of them is acceleration by gravity at the surface of the star, and the other is the equatorial centrifugal acceleration. We're going to use a slightly more complex approach, and you should definitely read these notes if you're interested in this, because it turns out if you take into account radiation pressure and also the fact that as a star spins, more material is going to end up on the equator, so that it gets kind of squashed. There's an extra constant factor of 2/3 that's going to show up in our code. With that caveat out of the way, we'll go ahead and set this up. So we'll say big G is actually constant dot G. This is, once again, so great. So happy that AstroPi has built this in. Just wonderful. Don't have to worry about the value of that. Don't even have to worry about the units. It will just handle it. We're going to say that the mass is 1 times u dot m underscore sun. Again, just wonderful to pull that value in. Radius is 1 times u dot r underscore sun. And then we're going to do this. This is the result of setting those two equations equal. So we've done a slight amount of simplification here, but this will give us, again, by setting that acceleration caused by the being a spinning object going around versus the acceleration due to gravity, this is the equation that will pop up, and you can see the derivation in those notes that I have linked. So it's 2/3. This is the magic factor that you get from including some more complex factors that we talked about, times G times M. I actually made a typo when I did this earlier, and I thought the typo was so interesting that I have chosen to repeat it. I'm going to type times R. This is not correct. We will fix it momentarily, but I want to leave that in there. And then we'll say to the power 0.5, so square root. The period then is this velocity, or I suppose it is the circumference of this star divided by the velocity that things are going around it. So the circumference is 2 times pi times the radius. If we divide by the velocity, well, there we go. We have our period. What I'm then going to do is convert this to u dot day. And oh no, an error. What went wrong? Well, if you scroll to the bottom, you'll see unit conversion error. This mess and time are not convertible. And in fact, it's because I did this, right? I said we were going to make a typo. When you divide by r, you get the much more sensible result of 0.114 days. And so I just think it's interesting, and I wanted to highlight how great AstroPi.units is for, 1, having all of this information in here, and 2, catching mistakes like that. It's really great that it does things. It just, at least for me, I find it to be extremely useful. Now, this next step is trying to be considerate of the fact that we're actually not talking about the sun. A lot of these stars, and in fact, I think the entire subset of them are actually M dwarfs. So we probably shouldn't be using these values that we've used for the sun. A very pessimistic estimate might be to say that these stars could rotate 100 times faster without breaking up. So we're letting this RM factor very, of order 10,000, which, given what we know about the mass radius relationship of stars and thinking about the HR diagram, yeah, I mean, we probably have included a ton of different kinds of stars that we're likely to include. We probably should tailor this more to M dwarfs. What we'll do is I'll show both things. So we'll start by following the advice I say above of a fudge factor of 100. Minimum period is this period stated above, divided by 100. And then we're just going to do what we've done before. Periodogram is LC1, dot normalize, units, parts per million, do a dot to periodogram. Maximum period is the max period. Minimum period is the min period. And of course, bg dot plt on a log scale. Cool. So when we run this, you'll notice we basically trimmed everything, right? This last peak, we kind of get half of it, but it's cut off the rest of the way. In fact, we really don't need to be so pessimistic about this. This ratio, when we're thinking about this R times M, is really not actually likely to vary by this wildly pessimistic factor that we've done. And so if you don't limit it artificially, you get something more like this, which might seem less believable given how much we've trimmed out of it, but actually you can see that this top peak here, or this highest peak that we identified as the most likely value for the true rotation speed, is actually the correct value, and we've in fact just excluded some of the aliasing. Now, you might be thinking to yourself, well, that's great, but why is he going on about this? How does he know that? And I know that because if you do this period that we just calculated, the physical limit on the period, and you do a dot to u dot day, sorry, we'll do to second, which is not how this works. This physical limit that we've set is much higher than the actual sampling rate of TESS. So this is actually the more relevant characteristic. And in fact, since the sampling rate of TESS it samples every 2 minutes for this sector, which means that we could at best expect to see something that has a periodicity of 4 minutes. So we might expect to see that. And if we do this period divided by 100 business that I was talking about, well, in fact, in case you want the math to be done for you, if I do 4 times u dot min to u dot second, 240, right? So our limit is of this fudge factor of 100 is maybe not the most helpful thing, and in fact, it's actually constrained by the detector itself. Okay, so I've really been hammering home on this point of like picking the correct boundaries for your periodogram, and I just want to emphasize the reason why I am diving into such great detail about this is that it is important, because if you don't do this, then you might end up with aliased peaks like we saw above. None of those peaks on the left side were actually real. They were just an artifact of the value that we selected. And it means you now have to, one, deal with those peaks after the computation is done, and two, you have to spend more computation calculating this stuff. And you might think to yourself, well, what does it matter if I'm looking at one light curve? And you're right. If you are looking at one light curve, do whatever you want, you'll get your answer. But a lot of people are wanting to look at more than one light curve. And so if you are interested in looking at 100, 1,000, 10,000, every TESS light curve, you really do have to think about this stuff. Both, again, just from the perspective of automation and having the data in the best possible form so that it's easy to parse, and also computational expense. And that is why I keep harping on and on about this. I will leave that there for now, and I hope that this has given you some things to think about, some motivations for setting the upper and lower boundaries of this, and that you can take it and apply it to whatever your science or area of interest is in the future. And again, this applies to things outside of astronomy too. The Nyquist is very ubiquitous in many fields. All right, I really spent a lot of time talking about that, and I see what time it is now, so we are going to have to dive right back into this lesson and keep going. There's some more information here about other things we could be detecting, notably binary stars. Those signals could be appearing in here as well, which are not really astrophysical signals. Also, the stars pulsate for more reasons than just that they're spinning. There's many different types of stars that pulsate for different through different physical mechanisms. Delta Scuti stars are famous for this. We're just going to assume that we found the rotation when we see whatever this period is. That's maybe not always correct, but we can try to make this assertion that, well, it's probably rotation, and if it's not rotation, it's pulsing on some rate, and so those pulses, we can think about it in terms of interesting stellar activity. We're comparing that with the flare rate. To do that, we have to start, if we want to do this on a population level, we need to write functions because we cannot do what we just did for across dozens of stars. It would just take too long. This function just takes everything we've already done and wraps it up into one thing. So given the name of a star in the form of a tick ID, it's going to return the period at maximum power. So this turns the tick ID into that rotation rate. Our analysis is going to be based on a population of stars from a different notebook. And this notebook is one that actually trains the machine learning model to recognize flares, but they also have a pretty good collection of targets. So that's why we're going to borrow it. We'll do a file is tarfile.open to call down, whoopsies, download file, pass the file URL. Cache is true because I think I have a cached copy in my directory. File.extract all, oopsies, in this directory, and then file.close. Just, good practice. Close file handles when you're done. Oh, what have I done? There's an underscore. Permission denied. Oh, permission might be denied because I already have everything here and it's mad at me for trying to download stuff again. Yep. I think all of you should be having no issues with this, provided that you didn't already run this notebook. So I'm going to proceed because it's certainly there. I see the file in the directory in mine. And so if you don't, this is the cell to run to get that. Okay, let's just open it. So we've got the location where it's stored, catalog. We'll read in with astropy.io.ascii.read. Data directory plus the file name. And let's look at the catalog. 8,695 stars, information in here, including information about whether there is a flare. You can see that in this catalog, where the peak might be, amplitude of this kind of these different activities. So really, we're actually just interested in the tick IDs, and that's the whole reason that we loaded in this catalog because it's got interesting ones. So let's extract those. Stars are catalog, just the tick dot data, and we'll print that out to make sure it makes sense. String of numbers, perfect. That looks like a tick ID to me. Now we need to apply this to the population. And so the whole population is quite large. And you also notice that some of these values here repeat. But if we only use the 200th star, then the calculation will only take a couple of minutes. So what we'll do is we'll say that rotation rates is just an empty list that we're going to fill. For star in, somebody suggested last time this package, and indeed we actually use it in this notebook, TQDM, which is just going to make a nice little progress bar for us as we go through stars. Now, I know I say every 200th star up there, but it's actually going to take us a while if we do every 200th, so I'm actually going to write 1,000 here, because that will get us a quick answer, and we are ever so slightly pressed for time. So for star in every 1,000th star, the rotation rate is, we'll call this function that we used above, calculate the rotation rate. We'll pass in, I don't actually think you need to pass in the star as a string, but it's in my notes that way, and I would really hate for it to not run. So I will pass it in as a string, and then we'll say that rotation rates plus equals the rotation rate that we just got. So that should append it to our list. When I run this, Every single time I have run this query today, I have to run it twice. The first time I get rejected by the MAST archive, uh, who apparently don't like how much data I've been downloading, and so I have to cancel it and do it again. And then it is just, don't do plus minus, do plus equals. And then it is just happy to resolve my query. So this only gives us 9 targets. It's not a whole lot. And in fact, the plot we are going to make afterwards is therefore slightly unimpressive, given that we have 9 data points. But it's fine. You'll be able to see the basic trend. And in fact, let's plot this. So not a huge distribution of periods. It's basically everything less than 2 days. That's where all of our targets fall. Again, we picked 9 targets, so you know it shouldn't be too surprising. Um, and if you do run this with the full notebook, which I recommend, it just takes a little bit longer, you'll see that the longer period objects actually do show up. This histogram populates quite nicely. Okay, very quickly, we're going to talk about assessing flares. And to do that, we're going to use the Stella package, which we'll use all the defaults for, basically, and we'll just run it on our data. What we'll do is say that CNN underscore Stella, so convolutional neural network Stella, is Stella dot convolutional neural network. It's going to output a whole bunch of files. So what we'll do is just tell it to put those in the data directory. That's where we just downloaded and unpacked a whole bunch of stuff, but it's fine. We don't need anything in there. So let's shove it in there. Keep our main directory clean. To test that our classifier is working correctly, now that we've set it up, we'll pass it this model for it to use, and then we just need to give it all of the time information and the flux information. So we'll say that our times is lc1.time.value, and then our fluxes is lc1.flux. You know, my notes say to put in the error here, but I know that the TESS error is actually not very good, and I wonder what happens if you run this without passing in the error. That's why my notes say this, because it demands it. Okay, errors is lc1.flux underscore error. There's so many warnings that show up. We'll talk about why these show up in just a second. But it's fine. Yeah, it processed something. And we're gonna see exactly what it processed by extracting all this information. Now the times and the fluxes that are in here actually are the same times and fluxes that we put in, but just to show you how you get stuff out of Stella, times equals CNN underscore Stella dot predict time 0 because we want the value. Fluxes is CNN underscore Stella dot predict flux 0 because we just want the value. And the prediction is CNN underscore Stella dot predictions, plural. When we run this, this is a pretty nice graph, if I do say so myself. The color scheme diverges, so the purple colored points are the ones that Stella has assessed as being likely to be a flare. And so if you think about this as a binary classification, these are the yeses, and the oranges are a no. Just on first glance, I see a lot of orange down here at the bottom, so good job, Stella. And I see 2 very large purple peaks, so it's working. We'll zoom in on one particular peaky part of this graph just to make sure, and you can see that, yeah, it does actually a pretty decent job of identifying when the flare is. This is pretty classic flare shape to have this dramatic up followed by a slightly slower, more steady downward curve. I will also note that it identifies some things as flares which are not flares, and that's okay. It's not perfectly trained, but it is good enough to do what we needed to do next, which is basically assess the flaring rate of each star. So you would just look at all of these points and say, well, of the total length of points, how many of them are a yes? Our threshold for yes is, we're going to say 0.5. I think that that's a reasonable estimate. It's going to include some of these points which don't belong, but it will get us close enough to do to do an interesting analysis. The flare cutoff value is 0.5. Again, that's the point at which it goes from yes to no. The total length is just the length of the prediction. The flaring length is, I'm going to try something slightly different here than my notes, is actually just the sum of all the places where the predictions are greater than the flare cutoff. So flare cutoff. I think in order to actually make this comparison, we need to do zero indexing. So we're comparing a value. And then this will give us a list of trues and falses. And when you sum over it, it only adds up the trues. We're going to see if that works. If it doesn't, I'm going to just resort to what my notes say. So the fraction flaring is therefore the flaring length divided by the total length. Prediction, dang it. Prediction singular is the name of that variable. Oh no, numpy.bool object is not iterable. That's fine. Okay. Womp womp. I really did want that to work. That's totally fine. We'll just do prediction. So we're just doing an index on that now, and we'll just ask what the length of it is, which is fine. That flaring length is not defined because I don't know how to spell. Cool. We're going to create a plot of this result now. So we'll do a plot.scatter, pg period, oopsies, period. If I still can't spell, period at max power. And then the fraction flaring. Now, you might be thinking to yourself, this is going to be an unimpressive graph. And you are correct. We have precisely 1 point. So not that interesting, but we can expand this to an entire population. Again, if we just repeat what we've done above, such that you pass in a name and you get out a flaring rate based on the same model, we can assess the flaring rates for all of our targets. So for star in every 1,000 stars, the flare rate is calculate, flare rate. And we'll pass in star name as a string. Again, I don't know that that's actually necessary. Flare rates plus equals the current flare rate that we've calculated, and that should give us a nice array. Oh my gosh, MAST, let me make a query, please. Okay, good. These are the warnings I expect to see. I see what time it is, so I'm going to start steering us toward the conclusion and also briefly talk about why this is spitting out so many errors. I am a big fan of open source software. I think it's a great way for the astronomy community to collaborate, and I am very grateful to the authors of the Stella package for writing it. However, one author has sole access to the Git repository where this is stored and just will not merge pull requests. So there are some updates to Stella that need to happen that just haven't happened. And all of these errors are being thrown because we're on a newer version of software than when it was written 4 years ago, and so things have been deprecated. It still works for now, but at some point, this package might be forked and someone else might just take over the ownership, which is a benefit of open source software, right? No one really holds the key. You can copy and create your own. And when we plot this, we do actually get a nice distribution of flare rates here. So most of them don't do a whole lot of flaring, but there's definitely one star that seems to be doing a whole lot, or at least Stella thinks it's doing a whole lot. And we can create a plot of this to compare what those look like. Now, looking at this, you might go, I'm not particularly convinced by that. But if we do the astronomy magic of, well, maybe it's a power law, and we take the log of both of these, it's slightly more convincing. It would be even more convincing if we had more of our targets available. If we did the full sample here, which we're not doing, which is fine. There are some more cells down below. I see that I have basically a minute left here. I'll quickly copy paste the code in, but basically all that we're doing is just calculating what a regression for this would look like, and what's cleaning up any unrealistic values. There are no unrealistic values that come out of this particular analysis. When you do the full set, I think there are a couple. Oh, good, I didn't import SciPy. But when you run this, you can get a regression here. There's more data cleaning that happens below. Some of these points actually shouldn't be included because of limitations in the Stella package. But the point here is, when you look at this graph, the longer period objects spend less time flaring. Slowly spinning objects don't flare as much. Shorter period objects, that is, things that spin more quickly, spend more time flaring. And in fact, this trend is more or less exactly what we expected, and also is pretty robust even as you add more data. I see that I'm out of time, so I do want to just make sure that I have a moment to answer any questions that people might have. Maybe I'll run some cells just so we can talk about, these points getting excluded and the regenerated fit for the line. But that's basically it for this lesson. Next time on the webinar, what we'll do is we'll dive a little bit deeper into the statistics, because drawing a trend line on a graph does not an actual relationship make. And so we'll just think a little bit more about how we could introduce some more rigor and the level of confidence with which we can claim to have found this relationship. That's on the agenda for next time. Additional exercises if you're curious. Thanks everybody for coming. I think I will leave it there for now, and I hope to see you all at the session next week.